So hello friends, welcome to our channel. Today let's see about Galois field. So basically this starts okay. This is spelled as actually Galois field, but we have to pronounce it as Galois field. So basically this is a field of f. It is a set of elements with two operations, addition or multiplication, satisfying the following properties. So in this field there will be elements. Okay, for example, a Galois field consists of two elements. Let it be A and B. It is a set of elements. Those elements are A and B. So that A and B should satisfy these properties. Like first, if f is a closed under plus and into dot is a multiplication, that is a plus b and a into b are in f, if a and b are in f. That means, for example, a and b, if you multiply, I need to get again a or b. That means the values of addition or multiplication, or the results of addition and multiplication, those values should be present in that set of elements. Okay, for example, let us take a Galois field of 2, where you can see it is the Galois field of 2 is made of two elements, that is 0 and 1. So in this, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0. Actually this is a mistake. So you can see that here. Okay, so 1 plus 1 is 0. Because this is not an addition, we will do arithmetic modulo, or the modulo to arithmetic. That means XOR operation basically. So 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, and 1 XOR 1 is 0. So that's all. So same way here also, 0 into 0 0, 0 into 1 1, 0 into 1 is 0, 1 into 0 0, 0 1 into 1 is 1. So if you see the results, these are also the results we got are also in the set of 0 and 1, right? So you got 0 and 1, that's it. There is no other number that is present. So that's it. Now this is the Galois field of 2. Okay, like that, that first statement states that. Now coming to the second statement, commutative law, that is a plus b is equals to b plus c, and a into b is equals to b into a. Now associative law, a plus b plus c is equals to a plus b plus c. When coming to the multiplication, a into bc is equals to ab into c. Distributive law, a into b plus c is equals to a into b plus a into c. Now further in the identity, there are few other properties called identity of elements 0 and 1 must exist in f and f. Okay, the identity of 0 is a plus 0, that is a, right? So that a also present in the element only. Now a into 1 is a. So this is what. Now for any a in f, there exists an additive inverse a minus a such that a plus of minus a is equal to 0. Actually a plus a. Okay, yeah. From here it is the same one line. So a plus of minus a is equal to 0. A minus a is equal like that. But basically, as if it is in a modulo 2 arithmetic, either plus or like a plus a or a minus a will be resulting to 0 only. There is no such significance for plus and minus. Now coming to, for any a in f, there exists a multiplicative inverse a inverse such that a into a inverse is 1. So these are 8 properties. Okay, so the above properties are true for a field with both finite as well as infinite elements. In a field with a finite number of elements, say q, there are q Galois field elements. That is here actually we can see there are only 2 elements, 0 and 1, whereas now we are taking some q elements are there. For that, it's called a Galois field. Is denoted by g of f of q. If there are q elements, then you will say gf of q. If there are 2 elements, gf of q is gf of 2. So if only the first 7 properties are satisfied, then it is called a ring. So when only up to this point it is satisfied, up to till the 7th point it is satisfied, then we call it as ring. So we can see the tables for Galois field of 2. Okay, so similarly we can see I think it's not here, we can see Galois field of 3 table. So basically how these values will get, we will be seeing later. Basically this Galois field of 3 is not an important, but we will see. Galois field of 4 also, Galois field of 4, that's why we had 0 1 2 3, and you can observe, by observation you can see that as in Galois field of 4 there are 0 1 2 also, that means Galois field of 3 elements are also present. Galois field of 3 elements are 0 1 2. In Galois field of 3 we can see 0 and 1, either here also we can see 0 and 1. That means basically those are all the number q which are less than q will have the subset, make a subsets of it. Like see 0 1 2 will be present in this, and 0 1 also will be present in the higher orders. So here we can see those are the subsets, right? Now basically we will after a few lectures we will see how we got this matrix, values of this matrix, not values of the matrix, basically the elements. For g of f we wrote the 0 1 x and x plus 1, right? After a few lectures we'll know how we got this. Okay, so on internal these are also we'll see. So basically 0 plus 0 is 0, XOR no, 0 XOR 1 is 1, 0 XOR x is x, and 0 plus x plus 1 is x plus 1. Same for 1 plus 0 1, 1 plus 1 XOR 1 is 0, 1 plus x is x plus 1, 1 plus x is actually x. How we got x is here we will see, we'll get this topic. Okay, I think I explained it. So actually from the above we know that how these will be, the equations will be simplified, right? How will, when there is any repetition we'll take it out, right? When it repeated 2 times, same way. So here we can see that x plus 1 plus 1, right? So this plus 1 will be become 0 and will left with x only. So like that. Okay, and now coming to the product also the same way, x into x is x square. Actually x into x should be x square, but when deriving we'll understand why it is x plus 1. Okay, and yeah, that's it. So next is primitive polynomial. So primitive polynomial, it is basically primitive polynomials is a polynomial that should, first the polynomial should be irreducible. Then for a irreducible polynomial we'll see whether it is a primitive or not. So first we need to check whether the given polynomial is irreducible or not. So how to find that whether it is irreducible or not is okay. So how to find whether it is irreducible or not, we'll see here. So basically where is it? So how to do this work? For example, for a given polynomial m is the highest degree of a polynomial. For example, in this instant we'll see here we can see that is p of x is x power 4 plus x cube plus x square plus x plus 1. Here the highest polynomial is 4, right? So m will be 4. So first we need to find the polynomial that is x power 2 power m minus 1 plus 1. So m is 4, right? 2 power 16 minus 1 plus 1, that is 2 power 15 plus 1, sorry, x power 15 plus 1. So this is one of the polynomial with a degree 15, right? Now what we have to do, we have to divide this polynomial x power 15 plus 1 with p of x, that is x power 4 plus x cube plus x square plus x plus 1. After dividing we will see so if it is divisible, that means if you got a remainder as 0, then we can say that the p of x is a irreducible. Okay, so that's what. If for example if you take another example here, in this example here x cube plus x plus 1, if you take this example, when you take this is m is 3, right? 2 power 3 minus 1, that is 7, x power 7 plus 1. So we will divide that with x and it is divisible, so it is primitive. So remember, if the p of x is able to divide that x power 2m minus 1 plus 1, then we'll tell that p of x as as irreducible polynomial. Now we have to see how we have to check for primitive. So to check for primitive, it is not an easy way. Basically it is a time taking process, but hit and trial method. So how we'll do? So actually the maximum value of this p of the maximum degree, highest degree is 3, right? So now what we have to do, from 3 we need to so what we'll do, from 3 you need to start. So let us take a polynomial that is 3x plus 1, which has a degree of 3, right? We will divide this polynomial with the given x p of x. Okay, we'll what and all we have to do. From here you have to increase the one by one. First you will take 3, next you will take 4, 5, 6, 7 till up to 2 power m minus 1. So that is n value. That means in this case up to 7 we need to do. Okay, so then up to 7 we need to do. But if you see that basically how we will divide, so first we take x cube plus 1, that is divided by this given p of x, and then if it is divisible, next we have to see whether the given that what we have considered is divisible, is able to get divided by this. If it is divided, then we'll say it is not primitive. If it is not able to divide, then we'll say what to call if it is able to divide, then it will say not primitive. If it is not divisible, then we'll say primitive. Okay, remember that. First step is irreducible. How to find? We'll divide that 2 power x power 2 power m minus 1 divided by the p of x given. Now if it is able to divisible, if it is if the remainder r of x is equal to 0, we call it as then it is irreducible. If r of x is not equal to 0, that is a remainder polynomial. Okay, the remainder is not equal to 0, we go non-irreducible. Okay, this is clear, right? So coming to that what you call primitive, how to say the primitive. For example, the given question, that is x power q 3 plus x plus 1. For this the m value is 3, right? So m is equals to 3. From what you have to take, let us take an example from, so basically you need to take from m to n greater than 2 power then should be greater than m less than or equal to 2 power m minus 1. Yeah, 2 power m yes, so 2 power m minus 1. So what happened, from 3 will start from, so we'll take x square x cube plus 1 divided by that p of x. Next x power 4 plus 1 p of x. Basically I am using only this one, x power m plus 1. It is not necessary that only this will take. We have to see for all the possible combinations. So basically how do we know the possible combinations, how many we'll get is I will show you here. So for at the beginning we'll see that. So for a degree, for a Galois field of 2 with a degree of m, okay, for example there is this I think it's in the slides. So basically if you want to write the polynomials over G of a Galois field of 2 with a degree of 2, with a degree sum 2, okay, the formula is how many polynomials will get is 2 power this degree, that is 4, right? So how do we know? That means generally a Galois field of 2 with a degree m, in the question in the exam they have asked means we need to find 2 power m. That means if for example if the degree is 3, that means we will get 8 possible polynomials with a degree of 3. Okay, you can see here that is an x square, right, with a degree 2. Yeah, this is satisfied. Next 1 plus x square with a degree 2, satisfied. X plus x square is the highest degree is 2. 1 plus x square, the highest degree is 2. You can check, there will be no other combination will be possible other than this 4 with a degree of x square. Okay, all will be present here only. Okay, as it is only Galois field of 2, the coefficient should be either 0 or 1. Okay, there should be no other like 1 plus 2x like that. No, it should not be there because the Galois field is 2. In the Galois field we will call it as also, we will call it as a binary field, as we will have only 0 and 1 binary bits. So that's how these are the combinations. So basically I am taking this one, 1 plus x power m, that is what I am taking. Yeah, actually we need to check for everything, like x square we need to check, x plus x square you need to check. If it is x power m, no, the possible combination will come, no, we will have to divide each one with the given p of x, and we need to increment that power also. First we need to first if it starts from m, degree of m we will start, next m plus 1 we will keep, m plus 2 will keep, like that. But in exam maybe they won't ask about that, but it is a concept, that's it. We won't use also by primitive and all, just if you know, we'll take that in like the next concepts, we will take a primitive polynomial directly. So that's why we are talking about this, what is a primitive polynomial. So in this so after knowing that, how do we understand it? So first this they will check for irreducible. If it is irreducible only, we'll check for primitive. If it is not irreducible, directly straightforward you can say it is primitive, it is not primitive. So for primitive I am taking one of the combination, that is x power m plus 1, that is in this example that is m is 3, right? So I am starting from x plus 1 divided by p of x, x cube x power 4 plus 1 by p of x. If at least 1 is divisible, then we will say it is not primitive. All these combinations till 2 power m minus 1, that is m, we increase that n is equal to 2 power m minus 1 till there, till this point. If none of the polynomials are able to divide all these sets of polynomials, then we will say it is a primitive. If it is able to at least one on this combination is divisible, then we will say it is not primitive. Okay, so basically that process is so hard. So what happened, they made the process easy by making a table where it will we can see all the this is a table that is made. Actually this is so not an easy process, right? Time taken. So what happened, for a particular value of m is equal to 3, 4, like that, they have given directly a primitive polynomial for m is equal to, primitive polynomial for when m is equal to 3, like that. But it is not the only one primitive polynomial, there might be another combination also, but this is one of them. Okay, it might be one, it might be more also. For m is equal to 3 we may get more primitive polynomials also, but this is one combination, like that. So like that, from m is equal to 24 they have given a table. Okay, so this is how we will say for primitive polynomials. So now let's see how to construction of Galois field. So what I told you, how to we'll draw the table for 0, 1, x and x plus 1. How we got that, we can see here. Basically let us take, and in general the elements, the field elements will be in the form of 0, 1, x square, so on, x power 2 power minus 2. Okay, this is the fashion, that is 0, 1, 2, 3, 4, like that we wrote, no? Those elements in the general form, it will be like this. Okay, here the alpha is basically the solution, is one of the solution of a primitive polynomial. Okay, is a root basically. So let us consider for gf of 4, where 4 can be written as 2 power m. Okay, for a 2 power so gf of 2 power m is 2, right? Here, because 4 and 2 square, so m is 2. The primitive polynomial is given as, for m is equal to what primitive polynomial from this table, 1 plus x square, right? So we took this, and let us consider that alpha is one of a root of p of x. Then we substitute alpha as x, so p of alpha is equals to alpha square plus x, alpha plus 1 is equal to 0, because it is a root, so it will be results to 0. Now what we'll write, in generally alpha square, when you want to move this to on the right hand side, alpha square will be minus of alpha plus 1, but it is a binary arithmetic, so what we will say, there will be no significance of minus here. So alpha square is equals to alpha plus 1 only, plus and minus are the same only, that's why alpha square is equals to alpha plus 1. Now let's calculate for alpha cube. Okay, alpha cube is alpha into alpha square. So when you multiply, we'll get as alpha square plus 1 alpha, and so basically alpha into alpha square is alpha plus alpha, and multiply internally, and we got alpha square plus alpha, where alpha square is alpha plus 1, and again alpha will be gone because XOR operation, and only 1 will be remain. But actually in this question, that is 2 square, so m is 2, right? When you substitute m is equal to, what is the value here? Alpha, till alpha square only we will get. Okay, that means 0, 1, alpha square only we will get. These are just for understanding, we have told here. Okay, so we'll see one. So basically the Galois field, we can see that is only we only require 0, 1, alpha and alpha square, because up to 4 only, no, 2 power 2 square at m is 2. So only these elements is in a Galois field, the set of elements is 0, 1, alpha and alpha square. So we write a table for it first. So power representation, when you write directly 0, 1, alpha and alpha square, we call it as power representation. Okay, we wrote this. Now polynomial representation. So polynomial representation, when you try to write, so polynomial will be in terms of x, no, so we need to substitute what is x for alpha. So 0, so when it actually this 0, that means there will be no x, right? So normal constant 0. Now 1 is a constant. When you want try to write this 1 as x, how to write? X power 0 is 1 only, no, so that's what x power 0, and the coefficient of x power 0 here is 1, like. Now alpha is equals to x, that is already we consider that only, no, so x, alpha is the root of x, so x power 1, that is x. Now coming to alpha square, where alpha square is called alpha plus 1, right? And the above relation here, from x square plus is equal to alpha plus 1, here we can see that what we substituted. So when you substitute for alpha, it is x plus 1, that is x square term is x plus 1. You understand, right, how we got x plus 1? So from that alpha square value is x plus 1, so that's why we got as 0, 1, x and x plus 1 for GF of 4. Now coming to the 2 tuple representation. 2 tuple because tuple is like set, and this 2 represents 2 bits. So basically how to write this? So basically, so it is 0, that means there is no x naught, the x, basically this is highest degree is what, 1, right? And that means 1 plus x, so 1 plus x, the maximum, that means there will be 2 coefficients, that is x naught and x power 1 coefficients. So here there are no coefficient for them, so both will be zeros. Now coming to here, x naught, that is from lower to higher we need to see, that means like lower degree to higher degree, 1 plus x square plus x square, like that. So from 1, so this will represent the coefficient of x naught, that is 1, and there is no x power 1 coefficient, that's why 0, 1, 0, and here there is no coefficient of x power 0, that's why 0, and x power 1 coefficient is 1, and here both are present, so 1 and 1. So basically it should be written as 1 plus x to avoid confusion. So x naught coefficient is 1 and x power 1 coefficient is 1 again. So that's why you wrote this table. Same way for a Galois field of 2 power cube, that is Galois field of 8. Okay, the same way, but it is m is equal to 3. What is the primitive polynomial? X cube plus x plus 1. Here x is alpha, now alpha is a root. What we'll do? Alpha cube plus alpha plus 1. So where we can see that alpha cube is equals to, that is equal to 0. Same way, where how here alpha square is equal to alpha plus 1, here alpha cube is equals to alpha plus 1. Okay, the alpha square will remain same. By normal calculation we can see substituted, so up to 6 we will get alpha power 6, because m is 3, no, so 2 power m minus 1. So in this general formula, what you know, 2 power m minus 2, 2 power m minus 2. So from that we'll see up to 6, alpha power 6 it will get. Okay, from 0, 1, alpha square, so on alpha power 6. The same way we wrote this table also. In this there is one more new thing he got, integer representation. So basically in this polynomial representation and binary representation, that is 3 tuple, 3 tuple we wrote, no, same way 3 type. So basically 2 type, or here 3 type, how to write in the lower to higher degree, 1 plus x, we write that from 0 to will be zeros. Here it is 1, x naught power term is 1, and there is no x and x square terms, so 0, 0, like that we wrote. But when you consider this bit stream, the MSB bit is on the here. In general actually it should be in the right, left side, leftmost, but here the rightmost bit is MSB and leftmost bit is LSB. That's why here if you consider it is 0 0, it is 1 0 0, but when you writing in the integer representation it is 0 0 1, that means 1, right? Like that 0 1 0 2 0 1 0 0 4. You understand how it is there? It is in the reverse order. We need to so we need to convert that and then we write in the 4. We got 4. So G 1 1 0 in the reverse is 0 1 1. In the reverse you need to write 3. Like that we wrote. And the exponential representation is the same form of power representation. Only directly we'll write. That means if it is 0 0, 1 is in the terms of x naught, right? X power 0. Alpha is x power 1. Alpha square is x square. Directly substitute x in it. Alpha cube is alpha cube, x cube. Alpha here we need to write all this. So power 4, x power 4, x power 5, x power 6. Here we didn't write, but we have to write here. Okay, forgot to write. So this is how we got the elements for. So when you try to write a table for a Galois field of 8, the elements on this and this will be what? So 0 1 x square 1 plus x plus x square x 1 plus x plus x square plus 1 plus x square. So these are the elements for this Galois field of 8. But when it comes to Galois field of 4, we found that these are 0 1 x and x plus 1. We know how we got these internal elements. Now substitute if you want a table like 0 1 2 3. So in the place of x, if you substitute 2, that is 0 1 2 and 2 plus 1 is 3. In the same way, wherever there is x, substitute 2, we'll get the values. So this is how we'll do. So in the next lecture we can see how to solve for cyclic codes. Okay, cyclic and conventional codes you can see in the next section. Thank you for watching. If you like the video, share and subscribe.